Hi, in this lesson, I want to go through some of the key features of metamorphic rocks. Some of the key ways we can recognise the rocks that are produced by metamorphic processes that we've talked about in previous lessons. For this lesson, you'll need the metamorphic rocks diagrams A3 sheet. And what I want you to do is I want you to annotate these diagrams as we go. Okay. Metamorphic rocks are classified, as is the case with igneous and sedimentary ones, by their mineral composition and their texture. And in particular, it's their texture that's important. We split these into two groups, what we call foliated rocks and those that are non-foliated. It might sound a bit weird to define something by a feature that it doesn't show, but perhaps it'll become clear when we start looking at some of these materials. Let's start by looking at foliated textures. So these are the rocks that are on the left-hand side of your handout. Now, foliation, as we've talked about before, is a planar fabric in a metamorphic rock. What that means is we have an alignment of minerals within a rock caused by those minerals growing at right angles to any pressure that's applied. In this particular case, you can see sheets of the bright blue muscovite mica sandwiched in between the grey quartz grains. So we can tell by looking at this rock that we've got this alignment because those muscovite crystals are all aligned in the same sort of direction, and that'll be at 90 degrees to the pressure that was applied to that rock. So clearly, a foliated texture is going to be one that grows where the pressure is high. So if we have a look at some of these rocks, this is our first one. This is slate. Now, slate is, if we look at it in thin section, there's not a great deal to say about it. It's extremely fine-grained. It was originally a mudstone that's been compressed and aligned. Now, sometimes where we get slightly elevated temperatures, we might see some chlorite minerals growing within this. But mostly within a slate, the mineralogy doesn't particularly change. So we'll still have the same quartz and clay minerals that were in the original mudstone. It's just this has been compressed, maybe compressed by as much as 30%. And the clay grains in particular within that rock have aligned to create the distinctive foliation within a slate that we call cleavage. But the amount of, or the grade of metamorphism of a slate is low. The next rock we need to consider is this. This is a schist. Again, the parent rock material here was a shale, mudstone. But here we can see that there's been a lot more recrystallization. If we look at a thin section, we can see mica within this rock along with the quartz grains. So these sheets of mica, this foliation of mica that makes this rock a schist. We call that foliation schistosity. These sheets of mica, which can often get folded because of the pressure, are an indication that temperature is higher in forming a schist than it is in a slate, because we've got recrystallization. We also have a bit of ductile deformation. The fact these foliations get bent tells us this rock was a bit soft. Our final foliated rock is this. This is gneiss. Now, gneiss, you can see, has bands of different coloured minerals within it. This particular example is from the Isle of Lewis and is the oldest rock in Britain, about 3,000 million years old. In thin section, and even sometimes in hand specimen, this rock can look igneous. It's completely recrystallized. It was originally again a mudstone, but there's absolutely no trace of mudstone left at all within this. The type of minerals we find in gneiss are the type of minerals we might find in an igneous rock. Feldspars, quartz, hornblende, some mica perhaps. But this rock, although at first glance it may look igneous, that banding, that arrangement of crystals within the rock tells us it's metamorphic. The crystals can even look interlocking. So it's really important to be wary about identifying this rock as igneous. The key thing, again, is the foliation. Now, for the non-foliated rocks, we see a series of grains or crystals within the rock that are fused together. There are a number of ways of recognizing this. Looking for 120-degree angles between crystal faces. Looking, as you can see, just to the top left of center here, grains that have looked like they've been melded together. These show us that these rocks don't cut, these crystals don't cut across each other. They're sort of all lumped together, and it shows us that heat is the main agent of metamorphism for these non-foliated rocks. This is what we call a granoblastic texture. If you look at some examples, this rock is a marble. This is what happens when we heat up limestone. And the limestone, or the calcite crystals, you can see these pale, almost pastel colours in this particular thin section, fuse together. Notice there's no orientation of these crystals. You know, the pressure acting on this rock when it formed was very low. We can get new minerals growing within these rocks. It isn't just about recrystallizing the minerals that are already there. This is an example, it's a terrible name for a rock, but it's a spotted rock, where we get crystals of a new mineral, one called Garnet, has grown within this rock because this rock is subjected to high levels of heat, but low levels of pressure. In a thin section, we just see new minerals growing called porphyroblasts. Sometimes these even will push out on the texture of the original rock. And there are some of these rocks that are a bit of a nightmare to identify. This is Hornfelds. This is baked mudstone. It looks like there are foliations in it, but there aren't. Those are remnants of the original bedding. It's a very tricky rock to identify, Hornfelds. You generally need to have context. You need to see where this rock has come from to be able to identify it. Otherwise, it falls into our dark, fine-grained, really hard to tell what it is identifications. Like I say, in this particular rock, you can even see it in the thin section there, the original bedding is preserved within the rock. It's what we call a relic structure. Okay. Those are the rocks we need to be familiar with. There are some distinctively metamorphic minerals, minerals that we don't find in other types of rock. We've talked already about mica, for example. Now, mica isn't specifically metamorphic. We find it in all sorts of different rocks. These minerals, though, are. First of these is Andalusite or chiastolite. As far as we're concerned, this is the same stuff. It certainly looks the same. There's another mineral called chlorite, and finally garnet. These three minerals are exclusively metamorphic. If we find them in a rock, we know we're looking at a metamorphic rock. Equally, though, if we don't find them in the rock, it doesn't mean the rock isn't metamorphic. Let's have a look at what these look like. If we start with Andalusite, Andalusite's a very, very distinctive mineral. It forms needle-like crystals within a rock. Those needles have a square cross-section. Very often within that cross-section, you'll see surrounded by a sort of a lighter coloured cross, there'll be a dark square. You really can't confuse Andalusite for anything else. Chlorite, on the other hand, isn't as distinctive, other than its colour. Chlorite has a very pale green colour, much paler, for example, than olivine, and lends sort of a green tinge or green spots to a poorly developed schist or maybe spots within a slate. But it's very rare to find crystals of chlorite, as you can see in the picture on the left. The last of our metamorphic minerals is garnet. Garnet is a very distinctive mineral. Beautiful 12-sided crystals with this deep, dark reddish brown colour. In thin section, it's black, light doesn't go through it at all. It's very, very distinctive stuff. Where we find garnet, we know we've had high temperature metamorphism. So, to conclude, metamorphic rocks have distinctive textures and compositions. We don't have quite the hard and fast rules we do, certainly with igneous rocks or even to an extent with sedimentary rocks. But that just means we need to take a little bit more care in our interpretation of these things. If we do, we can come up with some good identifications that will tell us a lot, for example, about the temperature and pressure that the rock's formed at. In fact, some of these minerals give us a really good indication of that. But that's for another lesson. I'll see you then.